Hello there and welcome to the Sleepy Explainer, where the universe is explained like a curious mind drifting into rest with a touch of an imaginary world. Today we're going to cook the question, what if the greatest story we've ever told about ourselves was never true? Close your eyes and picture the universe not as a fireball expanding into emptiness, but as something older, quieter and stranger. No single moment of birth, no instant where time itself was struck like a match. Instead, an eternal stage, with galaxies drifting across it like actors in a play that never had an opening night. The Big Bang is more than a scientific theory. It's the origin myth of our modern world. The moment we point to when asked, where did it all begin? But what if that beginning never happened? What if the cosmos had no birth at all, but simply always was? For a century, astronomers have repeated the tale. The universe exploded into being 13.8 billion years ago, carrying with it the seeds of stars, planets, and life. It is elegant, it is powerful, and it is comforting, because it gives us a beginning, a neat starting line. But there have always been whispers, doubts, observations that don't quite fit, galaxies too well formed too early, puzzles about why the cosmos looks so smooth when chaos should rule. To fix the gaps, cosmologists add patches, inflation, dark energy, mysterious ingredients that we cannot see, cannot touch, but must believe in for the story to hold. And here's the haunting thought. Maybe the story persists not because it's perfect, but because it's familiar. Because the human mind craves beginnings. We want a genesis, a first page, a single spark. So tonight, let's set that story aside. Let's imagine, for just a moment, a universe that never banged into being, but one that has always existed. A cosmos without a birth certificate. A reality that might stretch infinitely into the past, with mysteries deeper than we dare to believe. Because if the Big Bang never happened, then everything changes. Our timeline, our science, our place in the vastness. The question is not just what happened instead, but whether we are even ready to face it. The idea of a beginning wasn't always obvious. For most of human history, the universe was imagined as eternal, a steady dome of stars watching silently over our lives. But that illusion cracked in the 1920s, when a man with a telescope and an obsession changed everything. Edwin Hubble looked deep into the night sky and saw galaxies drifting apart, like embers carried away on the wind. The further he looked, the faster they seemed to flee. The evidence whispered a single conclusion. The universe was expanding. And if it's expanding, then run the clock backward. All those galaxies must once have been closer, closer still, until they were compressed into something unthinkably small, a point of pure density, a beginning. It was a Belgian priest and scientist, Georges Lemaitre, who dared to say it out loud. He called it the primeval atom, a universe that started with a single spark, unfolding into time and space. Not everyone believed him. In fact, some mocked the idea, calling it the Big Bang as a joke. But the name stuck, and over decades the evidence piled higher. The faint afterglow of microwave radiation, the so-called cosmic background, seemed to be the embers of that first fire. The abundance of hydrogen and helium scattered across galaxies matched the calculations of a hot beginning. Piece by piece, the theory solidified. It became not just an explanation, but the explanation. the origin story of modern science. And yet, the stronger a theory becomes, the heavier the burden it carries, because the universe doesn't always cooperate with our neat equations. Some galaxies appeared too mature, too quickly. The smoothness of the cosmos seemed unnatural, and the Big Bang had to be patched, repaired with new ideas. An era of inflation faster than light, invisible dark matter to hold galaxies together, mysterious dark energy to push them apart. Each fix made the theory stronger on paper, but stranger to our instincts. More and more, it asked us to believe in things we cannot see. So, we arrive at a crossroads. Was the Big Bang truly the universe's opening act? Or is it just the story we've chosen because it fits our craving for beginnings? But what if the universe never had a first spark? For centuries, philosophers dreamed of eternity, an endless cosmos with no birth and no death, just infinite cycles of change. And when the Big Bang Theory first appeared, not everyone welcomed it. Some scientists resisted, arguing that it sounded too much like religion, too much like a creation story dressed in math. In 1948, a group of brilliant minds, Herman Bondi, Thomas Gold, and Fred Hoyle, proposed something different, the steady-state theory. In their vision, the universe had always existed and would always exist, expanding forever but never thinning out. How? They imagined new matter quietly bubbling into existence, filling the gaps as galaxies drifted apart. No beginning, no end, just an eternal stage where stars and galaxies come and go, but the play itself never stops. For a while, the idea rivaled the Big Bang. It explained why the universe looked roughly the same no matter where you pointed your telescope. It offered comfort. No singular moment of creation. No need to explain what came before. But then the evidence began to betray it. The discovery of the cosmic microwave background in 1965 was a blow it could not recover from. A faint echo that spoke of a fiery origin. The steady-state model faded, but the human hunger for alternatives never did. Today, cosmologists have returned to those old instincts, sketching models where the universe expands and contracts like a heartbeat, bouncing through cycles of birth and rebirth. Others imagine a multiverse, an ocean of universes bubbling endlessly, where our Big Bang was just one wave among countless others. In these stories, beginnings are illusions, like ripples mistaken for the whole sea. And yet, each of these ideas stumbles against the same riddle. If there was no beginning, if time stretches forever backward, how did we ever arrive here, at this moment? Here's the puzzle. If time stretches backward forever, then why didn't we get stuck in that endless past? Why aren't we forever trapped before now? This is called the infinite regress problem, and it's one of the strangest riddles in physics. Imagine a line of dominoes falling, but the line has no first piece, just dominoes stretching back into eternity. How would the fall ever reach you? To escape this trap, scientists began to wonder, maybe time itself isn't what we think it is. In the 1980s, the physicist Alan Guth proposed something radical: inflation. Instead of a neat beginning, he imagined the universe ballooning out of a quantum seed in a fraction of a second. A seed so small, so unstable, that it popped into existence almost like a hiccup of the vacuum. From that tiny flicker came everything: galaxies, stars, you, me. But inflation raised new questions. If this quantum seed could appear once, why not over and over? Some physicists believe we might live in an eternal inflation multiverse, a cosmic foam where universes endlessly bubble up, collide, and die. Our Big Bang would just be one flicker among billions. And if that's true, then the question shifts. It's no longer, why did the Big Bang happen? But why this one? Why here? Why now? And why us? Every new idea leads to a stranger horizon. The closer scientists push, the more reality starts to look less like a neat clock ticking forward, and more like an infinite storm of possibilities, with no single beginning to point to. Picture the late 20th century. In quiet offices and chalk-dusted lecture halls, physicists argued over the biggest question of all. Did the universe truly begin? Or is the Big Bang just a chapter in something larger? For some, the Big Bang was elegant, simple, almost poetic. A single beginning, a clean birth of space and time. Others found that idea too neat, too fragile. If a universe can spark once, why not a million times? Alan Guth's inflation theory cracked open the door, but rivals rushed through it. Andre Linde painted a bolder picture, an eternal, chaotic inflation, where universes are constantly budding off like cosmic flowers. Some would live only microseconds. Others, like ours, would expand for billions of years. In Linde's vision, the Big Bang wasn't the event. It was an event, one of countless births in a cosmic family tree without roots. But not everyone agreed. Roger Penrose, a towering figure in mathematical physics, proposed something stranger still: conformal cyclic cosmology. In his mind, the universe doesn't die in heat death. It stretches, thins, and then, in that very emptiness, becomes indistinguishable from a new beginning. What looks like an ending is actually the start of another cosmic round. A universe after a universe. Circles without end. For scientists, these weren't just abstract puzzles. They were existential. Each theory reshaped what it meant to be human. Are we children of a singular event, a fragile miracle that will never repeat? Or are we just one voice in an eternal choir, destined to be sung again and again across infinite beginnings? The debates grew fierce, not only in conferences but in quiet letters, scribbled equations, and midnight doubts. The closer they came to understanding the beginning, the more the beginning slipped away. For all the grand theories, science is not built on imagination alone. It thrives on evidence, and when it comes to the beginning of everything, that evidence is faint, like whispers from a fire that burned billions of years ago. One of those whispers is the cosmic microwave background, the faint afterglow of the Big Bang. Discovered in 1965 by accident, it's often described as the universe's baby picture, a frozen imprint of a cosmos only 380,000 years old. To many, this was the smoking gun, proof the Big Bang really happened. A universe that began hot and dense, then cooled and expanded. But here's the twist. That same radiation could also fit into rival stories. Inflation predicts tiny fluctuations in the background, little ripples that seed galaxies. Detect those ripples, and inflation gains strength. But detect patterns that shouldn't be there, like echoes or rings, and maybe Penrose's cyclic cosmology is true. Maybe our universe really is one in a repeating chain. This is where the story gets electric. In 2014, a team announced they had found just such a signal. Gravitational waves imprinted in the background. Smoking gun evidence of inflation. Headlines screamed. We had glimpsed the moment of creation itself. But within months, the claim collapsed. The signal turned out to be dust. Cosmic dust drifting in our own galaxy. The grand proof was gone. And yet, the failure did not kill the dream. It sharpened it. Scientists kept refining their instruments. Satellites like Planck, observatories buried in Antarctic ice, telescopes tuned to hear the faintest hum of gravity itself. Each new scan of the cosmic background is like a fingerprint test. Does it match a single birth event, or does it hint at something stranger? A universe older, broader, and less final than we've dared to imagine. Because behind every equation and every telescope lies a haunting truth. If the Big Bang wasn't the beginning, then what came before is written into those tiny fluctuations of light, waiting for us to read them. If the Big Bang wasn't the first moment, then what was it? Here, science stretches into the almost mythical. And yet, these are not myths. They are mathematical possibilities, born out of physics pushed to its limits. Some researchers imagine the universe not as a single firework, but as a cosmic heartbeat, endlessly expanding, collapsing, and reborn. This is the bouncing cosmology. In this picture, the Big Bang was not a beginning, but a rebound, the echo of a universe that had collapsed under its own weight and then sprang back. Space and time do not vanish into nothingness, they cycle like breath. Others turn to string theory, where our universe might be a three-dimensional membrane floating in a higher dimensional space. In this vision, the Big Bang was not a singular event, but a collision, our brain slamming into another, releasing unimaginable energy. The explosion was not the start of everything, but the shudder of two vast sheets of reality brushing past each other. And then there are the quantum dreamers. They suggest that when you shrink the universe down to the smallest scales, smaller than atoms, smaller than quarks, the rules of quantum mechanics take over. Here, time itself could blur. The Big Bang becomes less of a violent eruption and more of a phase transition, like water turning into ice. A shift, a reordering in a cosmic quantum field. Each of these theories asks us to imagine that our beginning was not the beginning. That what we call creation is just one act in a play with no first scene. But what unites them is this. All agree that the Big Bang, as simple and singular as textbooks once painted it, is not enough. Something deeper set the stage. Something stranger carried the universe to the edge and then let it fall into being. And the search for that something continues, in mathematics, in telescopes, and in the restless curiosity of a species desperate to know where it came from. What if the deepest mystery isn't whether the Big Bang happened, but what kind of thing the universe even is? Step into the world of quantum cosmology, where physicists treat the entire universe the way we treat subatomic particles, as a wave function, shimmering with probabilities. In this view, the universe didn't explode into being, it simply resolved. Out of a cloud of possibilities, one particular reality crystallized, ours. But then comes a wilder suggestion. What if the universe is not made of matter or energy at the most fundamental level, but of information? This is the holographic principle, the idea that everything we see, touch, and measure may be nothing more than a projection, encoded on a vast, invisible surface at the edge of reality. Like a cosmic hard drive, storing the data of existence. And here's where it becomes even stranger. If that's true, the Big Bang itself could be reinterpreted, not as an explosion of matter, but as the moment when the program began to run. A cosmic line of code executed, and suddenly, here we are. Think about that for a moment. Every galaxy, every star, every atom in your body, all just part of a vast informational structure, written, stored, and evolving. If so, then asking, what came before the Big Bang, is a little like asking, what came before the first frame of a movie? The answer might be nothing, or everything. This is not just philosophy. Black hole physics hints at this informational universe. Quantum mechanics keeps whispering that reality is more like a calculation than a construction. Even Einstein's equations bend to suggest that space-time itself may be emergent, not fundamental, but derived. And so the question shifts again. Maybe the Big Bang didn't happen. Maybe it was a threshold, the moment when the cosmic algorithm booted up, when reality as we know it transitioned from potential into play. If the universe is a kind of program, then surely the code must leave traces. And indeed, it does. Look up at the night sky and, hidden behind the stars, lies a faint glow that cosmologists call the cosmic microwave background. It's the oldest light in the universe, a whisper from nearly 14 billion years ago. And for decades, it was hailed as the ultimate proof of the Big Bang, a perfect afterglow of a fiery birth. But here's where the puzzle deepens. The map of this background radiation isn't as smooth as we once thought. It has anomalies, cold spots too large to explain, alignments that seem oddly structured, almost as if the cosmos has a preferred direction. Some scientists brush these off as statistical noise, others whisper something more unsettling, that these are artifacts of a deeper process, fingerprints left behind by a universe that didn't explode, but unfolded. Then there's the problem of fine-tuning. The constants of physics, the speed of light, the strength of gravity, the charge of the electron, are so delicately balanced that if any were off by the tiniest fraction, stars would not burn, galaxies would not form, and life would be impossible. Was this balance just a cosmic accident, or is it evidence of a hidden architecture, the parameters of a simulation, set deliberately, or inevitably, at the threshold we call the Big Bang? And here's a twist. Even the expansion of the universe adds to the mystery. Observations show it's not slowing down, as gravity would suggest, but accelerating, as though pushed by a force we barely understand, something we call dark energy. Is this expansion truly evidence of a bang? Or could it be the unfolding of a deeper law, like the stretching of space within a mathematical equation, still running quietly beneath everything we see? One by one, the clues pile up. The strange radiation patterns, the impossible fine-tuning, the accelerating expansion. Each is like a loose thread tugging at the grand story we've been telling for nearly a century. And so the mystery grows. If these are the signs of a deeper reality, then maybe, just maybe, the Big Bang was not the beginning, but simply the interface, the place where we begin to perceive the universe, but not where it truly began. If the Big Bang wasn't the true beginning, then what was? This is where science becomes less like a settled textbook and more like a detective novel, with competing suspects, each offering a different origin story for the universe itself. One of the boldest ideas is the cyclic universe. In this picture, the cosmos doesn't begin or end, it breathes. Imagine the universe expanding outwards, galaxies pulling apart, stars fading, until one day, perhaps trillions of years from now, gravity begins to pull it all back together. Everything collapses inward in a cataclysm called the Big Crunch. And from that collapse, another expansion is born, another universe, another cycle, like a heartbeat across eternity. If true, then what we call the Big Bang was just one inhalation in an infinite rhythm. But another camp suggests something even stranger, the bouncing cosmology. Here, instead of a violent singularity, the universe contracts smoothly to a minimum size and then rebounds. No true beginning, no infinite density, just a bounce from one phase to another. Some physicists love this idea because it dodges the biggest problem of the Big Bang, that pesky singularity where physics breaks down. Instead of laws failing, they simply bend. Then there's eternal inflation, perhaps the most extravagant vision of all. In this theory, what we call our universe is just a bubble, floating in an endless froth of expanding space. Other bubbles, other universes, are forming all the time, each with different laws of physics, different constants, maybe even different versions of reality itself. In this view, the Big Bang was not the beginning of everything, but simply the moment our bubble formed. Out there, countless others are still being born. Each of these theories pushes against the old story, replacing a singular birth with something deeper, more expansive, maybe even more unsettling. But all share one idea, that the universe we know may not be the whole story. It may just be a chapter, a local event in something far older, stranger, and more endless than we've ever imagined. And if that's true, then the question becomes unavoidable. What existed before our chapter began? To ask what came before the Big Bang is like trying to read the opening lines of a book that may have been torn away. Yet scientists, ever stubborn, have found ways to peer at the faintest clues, whispers etched into the cosmos itself. One of the greatest sources of these whispers is the cosmic microwave background, the faint afterglow left over from the hot early universe. It looks like static on an old television screen, but hidden in its pattern are delicate ripples, like fingerprints from the first moments of reality. If the Big Bang really was the beginning, those fingerprints should match one story. If the universe bounced from an earlier phase, they might reveal scars from a cycle before ours. Then there are gravitational waves, ripples in space-time itself. Detectors like LIGO have already heard black holes colliding, but cosmologists dream of catching waves far older, imprinted not by stars or galaxies, but by the birth of the cosmos itself. Such a discovery would be like hearing the universe's very first heartbeat. And in underground labs and particle colliders, physicists are searching for exotic particles, the kind that could only have existed in the first trillionth of a second. Some are hunting for axions or signs of dark matter that might carry secrets of a pre-Big Bang universe. Each experiment is like a fishing line cast into the deep, hoping to reel in something that doesn't quite fit the Big Bang story we thought we knew. What's striking is how fragile these investigations are. They rely on faint signals, on noise teased out of data, on patience measured not in years, but in decades. And yet, piece by piece, they bring us closer to an answer. If one day the evidence points clearly toward a bounce, a cycle, or a multiverse, then our picture of reality will tilt forever. But evidence is a tricky thing. Sometimes the universe gives us just enough to tease, never enough to confirm, which leaves us with a haunting possibility. Maybe the true origin of everything lies beyond what science can reach. If science can take us almost to the very edge of the beginning, what waits on the other side? Some say this is where the story passes from physics into philosophy, where equations give way to imagination. For centuries, thinkers have wrestled with the same riddle. Why is there something instead of nothing? The Big Bang, as powerful as it is, answers how our universe evolved, but perhaps not why it exists at all. If the universe did not begin with a bang, then maybe it never began at all. Could reality itself be eternal, with no starting point, no first domino to topple? Some cosmologists propose a cyclic universe, one that expands, collapses, and is reborn again, endlessly. In this view, our universe is just the latest verse in an infinite song. Others suggest we live in a multiverse, a vast sea of universes bubbling into existence, each with its own laws of physics. If so, then our Big Bang might not be the beginning, just our beginning. But here's where things turn unsettling. If universes can exist without a clear origin, then the comforting idea of a single creation moment starts to dissolve. What replaces it is stranger, a reality with no outside, no before, no ultimate cause. This is the point where even the most rational scientists admit something remarkable. As Nobel Prize-winning physicist Steven Weinberg once said, "The more the universe seems comprehensible, the more it also seems pointless." Yet others take the opposite stance, that the very fact we are here to ask these questions means the universe is tuned, delicately, improbably, for life. So where does that leave us? On the edge of science, staring into the unknowable. And yet, the unknowable has always been fuel for human curiosity. What lies just beyond the reach of our telescopes and equations might still be the key to understanding who we are and why we're here. Long before telescopes, satellites, and the language of physics, people still asked the same question that troubles scientists today. Where did it all come from? And their answers, though wrapped in myth and poetry, were no less ambitious than our modern theories. In Mesopotamia, one of the world's first civilizations, the universe was said to have been born from a cosmic battle. The goddess Tiamat, representing the endless ocean of chaos, was slain, and from her divided body, the heavens and the earth were formed. Creation, in this view, was not gentle. It was violent, raw, and deeply human. Meanwhile, in ancient India, the Rig Veda whispered a different vision. Who really knows? Who can declare it? The gods came later than this world's creation. Who then knows whence it has arisen? Even thousands of years ago, people suspected that origins might forever remain a mystery, an unknowable secret. The Greeks offered another twist. The philosopher Anaximander suggested that everything came from the apeiron, an infinite, boundless source without beginning or end. In a sense, he described something surprisingly close to modern ideas of an eternal universe. Why does this matter? Because these myths and early philosophies reveal a striking truth. Humans have always struggled with the possibility that the universe has no simple beginning. Whether told through gods, chaos, or boundless infinity, the attempt was the same: to wrestle with the same question modern cosmologists face under the cold glow of data. And so, as we listen to these ancient voices, another realization dawns. Maybe the story of creation is not just about the universe, it is about us, about our restless need to explain, to connect, to weave meaning into the silence. If the ancients looked up at the stars and saw gods and battles, today we look through telescopes and see data streams, spectra, and cosmic microwave maps. But make no mistake, the stories we tell are still astonishingly mythic. Take the Big Bang itself. At its core, it claims that from nothing, or something so close to nothing that our minds struggle to picture it, came everything. Space itself burst into being. Time began ticking. Matter condensed from a searing sea of energy. It is the modern creation epic, with equations instead of poetry. And just like the myths of old, the Big Bang faces rivals. Some scientists argue that perhaps the universe did not begin at all. Instead, it may bounce, endlessly expanding, collapsing, and rebirthing itself in cycles across unimaginable time. That idea, called the cyclic universe, mirrors ancient visions of eternal renewal found in Hindu cosmology. Others suggest a multiverse, where our cosmos is just one bubble in an endless froth of universes, each bubble with its own laws, its own story, its own beginning, or maybe no beginning at all. Suddenly, our Big Bang feels less like the ultimate answer and more like a local chapter in an infinite book. The parallels are hard to ignore. The gods of the past have been replaced by mathematical symbols, yet the ambition is the same: to take the unfathomable and give it form, to take silence and fill it with meaning. And here's where it gets fascinating. While myths were preserved in sacred texts, our modern myths are written in the sky itself. Every photon, every faint whisper of microwave radiation becomes a verse in the ongoing story. But as we've learned, stories evolve, evidence sharpens. And just as the ancients revised their myths across generations, our modern cosmology too is facing questions that may force it to rewrite its epic. And so, just when the Big Bang seemed unshakable, the universe itself whispered back, "Something doesn't add up." Imagine a detective piecing together a crime scene. All the evidence lines up beautifully, until one stubborn clue refuses to fit. Cosmology has those stubborn clues too. One of the biggest is called the horizon problem. The universe today looks remarkably uniform, galaxies scattered far apart, but the background radiation glowing at almost exactly the same temperature everywhere. Yet according to physics, there hasn't been enough time since the Big Bang for distant regions of space to exchange information, or even heat. It's as if two people standing at opposite ends of the Earth are wearing matching shirts, without ever having spoken to one another. Coincidence? Or is something missing from the story? Then there's the flatness problem. The universe appears finely balanced, teetering between eternal expansion and ultimate collapse. But this balance is so delicate that, if the conditions at the start were even slightly different, today's cosmos would look nothing like it does. How could the universe have been born with such uncanny precision? And let's not forget the mystery of dark matter and dark energy, invisible forces that dominate the cosmos, yet remain unexplained. The Big Bang model accounts for much, but not for the invisible scaffolding that shapes galaxies, nor the strange repulsive force driving the universe to accelerate faster and faster. These aren't minor footnotes, they're cracks in the foundation. And just as myths once evolved when they failed to explain eclipses or storms, so too must our modern myth evolve when the evidence starts to resist it. The beauty is, science doesn't fear cracks. Cracks are where light enters, where revolutions begin. And those cracks in the Big Bang led to one of the most radical ideas in modern physics. An idea so bold it reshaped cosmology itself. That radical idea was inflation, the notion that in the tiniest sliver of a second after the universe's birth, space itself ballooned at a speed faster than light. Not just fast, unimaginably fast. In less than a trillionth of a second, what was once smaller than a proton stretched to sizes larger than our visible cosmos. At first, it sounds absurd. How can anything move faster than light? The answer lies in a subtle trick of physics. It wasn't matter racing across the universe. It was space itself expanding. And the rules of relativity don't limit the speed of space's stretching. Inflation was more than a wild idea. It was a brilliant patch. It explained the horizon problem. Distant parts of the universe look the same because, before inflation, they were once close enough to exchange heat and information. Then inflation ripped them apart. It solved the flatness problem too. Any curve or wobble in the geometry of the cosmos was stretched so wide, it now looks perfectly flat to us. Like a balloon inflated so large, any small patch of it feels like a flat sheet. But inflation wasn't just a fix. It predicted things we later found evidence for. Subtle patterns in the cosmic microwave background radiation, ripples frozen into that first afterglow of the universe. Those ripples became the seeds of galaxies, the fingerprints of cosmic expansion. And yet, inflation carried with it strange implications. If space could inflate once, what's stopping it from inflating again? Somewhere else, even now? Could our universe be only one bubble in an endless froth of universes? Suddenly, the cracks in the Big Bang hadn't just been patched. They had opened a door into a far stranger, more infinite reality than cosmologists first imagined. But here's the problem with inflation. Once you introduce it, you can't easily turn it off. If space expanded once, why wouldn't it keep expanding in other regions? The equations suggest that while inflation ended in our corner of the cosmos, it might still be raging on elsewhere. That means our universe could be just one bubble, surrounded by an endless foam of other universes, each with their own physics, their own histories, perhaps even their own versions of reality. This idea, called eternal inflation, is dazzling and unnerving all at once. It offers a way to explain why our universe seems so finely tuned for life. In an infinite froth of universes, some will naturally allow stars, planets, and chemistry to thrive. We just happen to live in one of the lucky ones. But it also comes with a deep paradox. If there are countless universes, then predicting anything about ours becomes nearly impossible. Are we just one statistical accident? How can science test a reality that, by definition, we can never reach? And then there's the human angle. For thousands of years, humanity asked, why is the universe the way it is? Inflation's answer might be, because in infinity, every possibility exists, and we're simply in one of them. For some scientists, that feels like giving up. For others, it's the most profound expansion of perspective since Copernicus. So inflation doesn't just patch the Big Bang, it complicates it. It solves mysteries, but leaves us with even bigger ones. Are we unique, or just one bubble adrift in a cosmic sea? But theories, no matter how dazzling, are only half the story. Science demands evidence. If inflation really happened, it wouldn't have left the universe pristine. It would have left scars, tiny imprints in the oldest light we can still see. That light is the cosmic microwave background, the faint afterglow of the Big Bang itself, stretched and cooled into microwaves over billions of years. To the naked eye, the night sky looks dark and empty. But if you tune into the right wavelength, the entire cosmos glows with this ancient radiation, a ghostly whisper from when the universe was just 380,000 years old. When scientists first mapped this background, they didn't see a smooth glow. They saw faint ripples, tiny fluctuations in temperature, only millionths of a degree different. But those ripples weren't random. They carried a pattern, as though the early universe had been shaken, stretched, and imprinted with invisible fingerprints. And here's the astonishing part. Those patterns matched almost perfectly what inflation predicted. Tiny quantum jitters, magnified to cosmic scales by runaway expansion, froze into place and later seeded the galaxies we see today. Every cluster of stars, every spiral galaxy, every world like ours, all born from microscopic fluctuations etched into the sky nearly 14 billion years ago. It's as if the universe itself left behind a cosmic birth certificate, one that quietly confirms inflation wasn't just a clever theory. It might actually be written into the fabric of the heavens. But here's where the story takes a turn. For all the elegance of inflation, for all the fingerprints etched in that ancient light, not everyone is convinced. Because science, unlike myth, doesn't rest on beauty alone. It demands proof, and proof is slippery when we're peering back nearly 14 billion years. The cosmic microwave background does seem to echo inflation's predictions, but when astronomers looked closer, far closer, they found patterns that didn't quite line up. Large swathes of the sky looked a little too uniform, while others showed alignments that seemed almost unnatural. One feature has been nicknamed the axis of evil, a strange cosmic asymmetry that inflation can't easily explain. And then there's the deepest problem. We still don't know what actually caused inflation. What energy field could have driven the universe to balloon faster than light? What force could ignite such an event, then vanish without a trace? Physicists call this the inflaton field, but it's a placeholder, a name for something that has never been observed. So we find ourselves caught in a paradox. Inflation explains so much, yet leaves us asking, did we trade one mystery for another? Did we replace the question, what happened before the Big Bang, with the equally unanswerable, what sparked inflation? The universe gives us clues, yes, but it also taunts us, hiding the engine that started everything. And this tension between what seems proven and what remains unknowable is where the real drama of cosmology lies. If inflation wasn't the final word, then what came next? The stage was suddenly wide open, and into that space poured a flood of rival ideas, some cautious, others breathtakingly bold. One of the most persistent challenges has been the idea of a cyclic universe. Imagine time not as a line with a beginning, but as a loop, endlessly repeating. In this vision, the Big Bang wasn't the birth of everything. It was just one bounce in a long chain of cosmic expansions and contractions. The universe, in this story, dies and is reborn forever, like a phoenix made of galaxies. Then came the ekpyrotic model, a theory born from string theory's strange mathematics. Here, our universe collides with another in a higher dimensional space. That cataclysm sparks a Big Bang, not once, but potentially many times across eternity. Suddenly, what looked like the unique birth of our cosmos becomes just one ripple in a vast, unseen ocean. And there's yet another contender, the quantum universe hypothesis, which suggests that what we call the Big Bang may have been nothing more than a quantum fluctuation, a tiny blip in a sea of timeless possibility. Out of nothing, governed by quantum law, a bubble of reality expands and becomes everything we know. Each of these theories tries to patch the gaps inflation leaves behind, but more importantly, they change the way we see ourselves. Are we the lucky accident of a single event, or one chapter in an infinite book written and rewritten across ages beyond imagination? The cracks in inflation didn't close the case, They opened the door, and on the other side was a universe far stranger and maybe far older than anyone had dared to imagine. But bold theories are only half the story. In science, imagination is nothing without evidence. And so the question becomes, if the Big Bang wasn't the absolute beginning, how would we know? What clues could the universe possibly leave behind? For physicists, the answer lies in the oldest relic of all, the cosmic microwave background, the faint afterglow of the early universe. Like fingerprints pressed into clay, this light carries subtle patterns, ripples, cold spots, alignments that could betray the true origin of our cosmos. For instance, if our universe really collided with another, as the ekpyrotic model suggests, we might see strange circular scars in the cosmic background, faint rings where the two realities brushed together. If the universe has cycled through endless expansions and contractions, we might catch echoes of those earlier bounces hidden in the way galaxies cluster across the sky. And if the Big Bang was just a quantum fluctuation, then the laws of quantum physics might predict tiny, telltale deviations in the randomness of that ancient light. Deviations so subtle that only the most sensitive detectors on Earth or in space could ever reveal them. This is why projects like Planck, WMAP, and now the James Webb Space Telescope aren't just tools for pretty pictures. They are crime scene investigators, sifting through evidence 13.8 billion years old. Every new measurement adds pressure. Either these alternative models will be forced into the shadows, or they'll gain the smoking gun they've been waiting for. And the strangest part? Some anomalies have already appeared. Odd alignments, unexpected cold spots, things the Big Bang model doesn't explain cleanly. For some researchers, these could be the cracks that let new theories in. So the hunt is on. Scientists aren't just gazing at the stars, they're reading them like detectives searching for the oldest confession in existence. Science, for all its elegance, is never free from conflict, and in cosmology, the courtroom is crowded. Each theory, Big Bang, cyclic universe, multiverse, steps forward like a witness with its own story to tell. But when their testimonies overlap, contradictions ignite. Proponents of the Big Bang insist their model remains the most successful. It explains the abundance of light elements like hydrogen and helium. It accounts for the near-perfect uniformity of the cosmic background. It predicts the expansion we observe in every galaxy's flight away from us. For them, the case is closed. The Big Bang is guilty of creation, beyond a reasonable doubt. But critics fire back. What about the horizon problem? The fact that opposite ends of the universe are eerily identical in temperature, even though they should never have been in contact. What about the flatness problem, where the universe seems perfectly balanced between eternal expansion and catastrophic collapse? The Big Bang answers these with the idea of inflation, a burst of exponential growth. Yet inflation itself raises more questions than it solves, like a witness who can't stop contradicting their own testimony. Then the cyclic model takes the stand. Its defenders argue the horizon and flatness problems vanish if our cosmos has been expanding and contracting forever. No need for mysterious inflation, just the steady rhythm of an eternal heartbeat. But skeptics counter, where is the proof of those previous cycles? If the universe has lived and died countless times, where are the scars? Enter the multiverse camp. They point to inflation not as a flaw, but as an opportunity. If space can balloon in one region, perhaps it balloons endlessly, spawning bubble universes beyond our view. Each bubble could hold its own laws of physics, its own cosmic story. For some, this is the most exciting possibility of all, but for others, it's a betrayal of science itself. After all, How do you test a theory when the evidence lies forever beyond our reach? And so the debates rage, in conference halls, in late-night arguments over blackboards, in the quiet lines of scientific papers. To outsiders, it might seem like chaos, but this clash is not weakness. It is the sound of science sharpening its blade, cutting closer to the truth. In a courtroom, evidence is king. And in science, the rules are no different. A theory, no matter how elegant, cannot survive on beauty alone. It must make predictions. Bold claims that can be tested against the universe itself. This is the crucible where ideas are proven or destroyed. For the Big Bang, one such prediction was the existence of the cosmic microwave background radiation, a faint afterglow from the universe's fiery birth. When Arno Penzias and Robert Wilson stumbled upon it in 1965, the Big Bang earned a devastating piece of evidence in its favour. The steady-state model, once its chief rival, all but collapsed under the weight of that discovery. But the game doesn't end there. Predictions must go further. Can the theory explain the distribution of galaxies across cosmic scales? Can it account for the delicate ratios of hydrogen to helium? Each time the universe answers yes, the Big Bang stands taller in the dock. Yet each unexplained anomaly, like dark matter, dark energy, or the mystery of what sparked inflation, chips away at its authority. Meanwhile, alternative models are judged by the same standard. The cyclic universe must explain why we see no fingerprints of past collapses. The multiverse must wrestle with a deeper problem. Can it ever be tested at all, or does it slip quietly from science into philosophy? And here lies the paradox. The very ideas that push science forward often tread the line between what is testable and what may forever remain beyond human reach. Some scientists embrace this uncertainty as a challenge, a sign that the next great leap awaits. Others warn that if a theory cannot, in principle, be disproven, it ceases to belong in the halls of science at all. This tension is not a weakness. It is the engine of discovery. For in the end, science is not about certainty, but about narrowing the field of possibilities, step by step, evidence by evidence. But the deeper we look, the more one unsettling truth emerges. Perhaps the universe is not obliged to follow our rules. What happens when the witness on the stand gives no answer at all? When the silence itself becomes the mystery? That's exactly where cosmology found itself in the late 20th century. For just as scientists were celebrating the triumph of the Big Bang, the universe revealed something unsettling, something that didn't fit the script. Galaxies were spinning far too quickly, their stars moving as though held by an invisible hand. According to the rules of physics, they should have flown apart like sparks from a fire, and yet they clung together. The missing glue was named dark matter, an unseen mass that outweighs all the stars, planets, and gas we can detect. Then came an even greater shock. In the 1990s, two teams racing to measure the universe's expansion discovered that it wasn't slowing down, as gravity should dictate. Instead, it was accelerating, as though some mysterious force, now called dark energy, was pushing space itself apart. Suddenly, the courtroom grew quiet. The leading theory, the Big Bang, still stood, but it was incomplete. The jury demanded answers, and all science could offer was placeholder names: dark matter and dark energy, labels for phenomena we barely understand. Together, they account for 95% of the cosmos. 95% of the universe is a question mark, and that realization reshaped the very tone of cosmology. The universe is not a solved puzzle, but a riddle still unfolding, where every answer only spawns deeper questions. We thought we had the ending to the story. Instead, we found a plot twist, And here's the thought that lingers like a whisper in the dark. What if this silence, these unanswered riddles, are not gaps waiting to be filled, but signs that our story itself is incomplete? And so the story continues, as though the curtain had lifted on an even stranger act. If dark matter and dark energy hold the universe together, or tear it apart, then where are they hiding? This question ignited one of the most ambitious hunts in modern science. All across the world, enormous detectors were buried deep underground, shielded from cosmic rays and noise, waiting for a single, ghost-like particle of dark matter to collide with ordinary matter. Months passed, then years, then decades, and the detectors remained silent. Meanwhile, in the skies, telescopes searched for the cosmic fingerprints of this unseen substance. They mapped the way galaxies bent light from objects behind them, a phenomenon called gravitational lensing. The results were breathtaking. Invisible halos of matter surrounding galaxies like phantom scaffolding. Unseen, but undeniable. And as for dark energy, scientists built entire missions, like the supernova cosmology project, to chart the acceleration of the universe. With each measurement, the case grew stronger. Some mysterious energy is stretching the fabric of reality. Yet, no telescope, no detector, no equation has told us what it actually is. It's as though the universe is teasing us, giving us undeniable clues, but never revealing its hand. And the deeper we look, the more it feels as if our cosmic detective story is written in invisible ink. Here's where the thought begins to stir uneasily. Maybe we're not just missing a few puzzle pieces. Maybe we're trying to solve the wrong puzzle altogether. Maybe the story we've told ourselves of a single explosive birth in the Big Bang is not the final word, but the prologue to something larger, something stranger. And here's where the mystery deepens. If our detectors stay silent and our equations break under the weight of the unknown, perhaps the fault lies not in the evidence, but in the story we've been telling. For nearly a century, the Big Bang has reigned as the ultimate origin tale. A blazing birth, a universe expanding ever since. But not everyone is convinced. In the 20th century, long before dark energy or dark matter puzzled us, scientists like Fred Hoyle dared to imagine a universe with no beginning at all. His steady-state theory proposed that the cosmos has always existed, eternal, unchanging in its large-scale structure. Matter, he suggested, is continuously created as the universe expands, filling in the gaps, keeping things looking the same forever. It sounded bold, it sounded elegant, and for a while it rivaled the Big Bang itself. Hoyle even coined the phrase Big Bang as a joke, a jab at an idea he thought absurd. But here's the twist. While his model eventually fell out of favour, replaced by the powerful evidence for a hot, dense, early universe, the seed of doubt never quite died. Because if dark matter and dark energy remain elusive, then maybe Hoyle was right about something bigger. Maybe the cosmos is far stranger and far less finite than we dared imagine. Other models began to surface, ones that painted the universe as a cyclic stage, endlessly expanding and contracting, breathing in and out across trillions of years. Some versions even suggested that what we call the Big Bang was not the beginning, but merely the rebound of a previous collapse. And as you listen to these theories, one unsettling thought lingers. If time itself has no beginning, then what does it mean to ask, what started it all? Maybe the question itself is flawed, born from our human craving for origins, for neat beginnings and tidy endings. The hunt for the invisible may not just be about missing particles, it might be about missing imagination. But if the universe did not begin, perhaps it pulses. Imagine this. Instead of a single fiery explosion, reality itself breathes, expanding and contracting across spans of time so vast that entire galaxies are born, burned out, and forgotten, only to rise again in the next cycle. This isn't just poetic speculation. Physicists have explored models where gravity and quantum fields conspire to create an oscillating cosmos. In one cycle, everything rushes outward, stars ignite, galaxies form, civilizations might even rise. But over unimaginable eons, the expansion slows, reverses, and collapses inward, compressing all matter and energy into a searing density. Then, at the final moment of collapse, rather than ending in silence, a new expansion erupts. A new Big Bang, though not the first, not the only, just the latest beat in an infinite rhythm. Others take this further. They imagine that our universe is just one bubble among many, a froth of countless pocket universes, each born from quantum fluctuations in a larger multiverse. Some of these universes might obey the same laws of physics we know. Others might play by entirely different rules, where stars never form, or where time itself flows in directions we cannot fathom. And here's the unnerving question. If such a multiverse exists, then the Big Bang wasn't the beginning of everything. It was the beginning of our bubble, just one in a sea without end. This perspective reshapes the mystery of dark matter and dark energy too. What if they're not flaws in our models, but hints that our patch of reality is stitched together with unseen rules borrowed from that wider multiverse? It's a dizzying vision. Universes budding, collapsing, and rebirthing, like cosmic waves crashing endlessly against the shores of time. But here's the challenge. Beautiful theories mean little without proof. So where do we look for signs that the universe might not have begun with a single, definitive Big Bang? The answer lies in the faintest whispers of the cosmos itself. Astronomers turn their gaze not to galaxies or blazing stars, but to the afterglow, the cosmic microwave background. It is the most ancient light we can see, released when the universe was barely 380,000 years old. To most, it looks like static. To scientists, it is a treasure map. If the Big Bang was the one true beginning, then this glow should bear a particular fingerprint. A nearly uniform spread of temperature across the sky, with tiny ripples seeded by quantum fluctuations. And indeed, that's what we find. But what if there are hidden scars in that glow? Some researchers suggest that cyclic universes could leave behind faint circles or distortions in the cosmic background, echoes of previous expansions and contractions. Others wonder if the unexplained cold spots we've observed might be hints of interaction with other universes, brushing against ours like shadows cast across dimensions. And then there's dark matter and dark energy, the great mysteries of modern cosmology. Together, they make up about 95% of the universe, yet we barely understand them. Could they be the fingerprints of something deeper? Laws of physics that belong to a universe before ours, or the pull of neighbouring universes we cannot see? Every observation, every anomaly, forces us to confront the same question. Are we misreading the evidence because we're assuming a Big Bang framework? Could the universe itself be urging us to think bigger, to imagine beyond the explosion? Science is built on evidence, but evidence is never as simple as it seems. The cosmic microwave background may look like confirmation of the Big Bang, but for many cosmologists, it also whispers contradictions. Every unexplained cold spot, every asymmetry is like a crack in the glass, not big enough to shatter the theory, but impossible to ignore. This is where cosmology becomes less about numbers on a graph and more about philosophy. Do we cling to the neatness of a single beginning because it feels intuitive? Or do we dare to step into models where beginnings don't exist, where the universe is eternal, cyclical, or even infinite in both directions? Imagine being one of those scientists. You've spent years, maybe decades, working with data that mostly fits the Big Bang. Your colleagues celebrate it as the crown jewel of modern physics, but late at night, staring at the faint irregularities in the background radiation, you feel an itch you can't scratch. What if the universe is telling us a different story, one we haven't yet learned how to read? This is the razor's edge of science. Certainty on one side, wonder and doubt on the other. The Big Bang remains the most successful model we've ever built, but its very success can blind us to other possibilities. After all, how many times in history have we declared something settled, only for a new discovery to flip the entire picture upside down? And here's the hook. What if we are standing on the brink of such a reversal right now? What if the evidence already exists, hidden in plain sight, waiting for the next daring mind to interpret it differently? History has a way of humbling us. Every time humanity thinks it has reached the pinnacle of knowledge, reality has a way of pulling the rug out from under our feet. Take the geocentric model. For centuries, Earth was thought to be the unmoving center of the cosmos. The logic was flawless, until Galileo's telescope revealed the moons of Jupiter dancing around a planet that wasn't Earth. A single discovery cracked open a worldview that had lasted for millennia. Or consider Newton. His laws of motion were so precise, they guided ships across oceans and predicted the paths of comets. For nearly 300 years, his universe of absolute space and time was unchallenged. And yet, Einstein came along and showed that space and time themselves were malleable, bending and stretching with gravity. Newton's brilliance wasn't wrong, but it wasn't the full story. Now ask yourself this: is the Big Bang our own version of geocentrism, or Newton's universe? A theory so successful, so convincing, that we forget it might one day be outgrown. The faint irregularities in the cosmic background, the puzzles about dark matter and dark energy, the unanswered question of what came before. These could be our Galilean moons, our Einsteinian revelations, quietly undermining what seems certain. And here's the dramatic twist. Revolutions in science don't just rewrite textbooks, they rewrite our sense of who we are, where we come from, and what the universe is capable of. If the Big Bang were to collapse under the weight of new evidence, it wouldn't just be a scientific correction. It would be a cultural earthquake, reshaping everything from cosmology to philosophy to religion. So, the question becomes, are we already standing at the dawn of the next great shift? And if so, what could possibly replace the story of a single, fiery beginning? If the Big Bang isn't the ultimate truth, what could possibly take its place? Science, after all, never leaves a vacuum. When one idea falters, others rush in to fill the space. And over the decades, astronomers have imagined bold alternatives, stories of the cosmos that are as strange as they are compelling. The first great challenger was the steady-state theory. In the 1940s, Fred Hoyle and his colleagues proposed a daring vision. The universe had no beginning, no end, and no creation event at all. Instead, matter was continuously formed, keeping the cosmos eternally young and unchanging on the largest scales. To Hoyle, this was far more elegant than a sudden explosion. Ironically, He even coined the phrase Big Bang as a joke, never expecting it to stick. Then came the cyclic universe. Imagine reality as a breathing cosmos, expanding and collapsing over unimaginable spans of time. In this view, our universe is just one heartbeat in an infinite rhythm. Countless big bangs and big crunches, each erasing and rewriting the cosmic script. Some modern physicists still explore this idea through theories of bouncing cosmologies, where a prior universe contracts and then rebounds into ours. But perhaps the boldest is conformal cyclic cosmology, championed by Nobel laureate Roger Penrose. According to him, the end of one universe, when everything has thinned into pure radiation, can, in a strange mathematical sense, be reinterpreted as the beginning of another. The death of one cosmos is the birth of the next, with no singular bang required. And here's the hook that makes these ideas so intriguing. Each of these rival theories isn't just abstract speculation. They claim to explain problems that the Big Bang still struggles with, from the mystery of dark energy to the uniformity of the cosmos. And some even hint at subtle signatures we might be able to detect today. So the real question isn't whether scientists can dream up alternatives, it's whether the universe itself is whispering clues that the Big Bang is not the full story. But if the Big Bang isn't the whole truth, where are the cracks in its foundation? Strangely enough, some of them are written across the heavens themselves. Faint signals that don't quite behave as they should. The most famous is the cosmic microwave background, often described as the afterglow of creation. When satellites like COBE, WMAP, and Planck mapped this faint radiation, they revealed a universe astonishingly smooth and uniform. Too smooth, in fact. For the Big Bang to explain it, cosmologists had to invent an extra chapter. The idea of cosmic inflation, a burst of faster-than-light expansion in the universe's first instant. Without it, the observed harmony doesn't make sense. But here's the problem. Inflation is still a hypothesis. We've never detected the smoking gun signals it predicts. Then, there are the large-scale structures of the universe. Immense walls of galaxies and vast cosmic voids. Some of these features are so enormous, they test the limits of what the Big Bang model says should be possible in just 13.8 billion years. It's as if the universe built cathedrals larger than the blueprints allow. And what about dark matter and dark energy? Together, they account for 95% of the cosmos, yet both remain invisible and unexplained. Big Bang cosmology includes them out of necessity, but each is a placeholder, a mystery we accept because without them, the equations don't work. To some scientists, this reliance on invisible scaffolding feels uncomfortably close to patchwork. Even the expansion of the universe itself presents a riddle. Different methods of measuring the Hubble constant, the cosmic expansion rate, give conflicting answers. This so-called Hubble tension has grown sharper in recent years, leading some to whisper that maybe, just maybe, our entire framework is missing something fundamental. So we're left with a paradox. The Big Bang model explains so much, yet at its edges, the universe seems to resist, hinting at deeper laws waiting to be uncovered. And so the question becomes, when the blueprint of the cosmos shows cracks, what do? You go looking for the missing pieces. Across the globe, physicists and astronomers have turned into detectives, chasing whispers of truth in data that most of us would overlook. Take the search for primordial gravitational waves, faint ripples in space-time that inflation theory predicts should still echo today. In 2014, a team at the South Pole thought they had found them, a discovery so monumental it would have rewritten textbooks overnight. But within months, the signal was revealed to be dust. Not ancient gravitational waves, but particles drifting through the Milky Way. For many scientists, that failure was sobering. The universe wasn't ready to yield its secrets so easily. Meanwhile, other teams are probing the Hubble tension with increasing precision. Telescopes like Hubble and Gaia measure local galaxies, while instruments like Planck analyze the ancient afterglow. Yet instead of closing the gap, the results keep drifting apart, deepening the mystery. It's like two clocks telling the time of the universe, but each refusing to agree. Which clock is wrong? Or is our whole calendar flawed? And then there's the hunt for dark matter. Deep underground, detectors filled with ultra-pure liquid xenon sit in silence, waiting for a particle that may never come. If dark matter is real, these machines should eventually hear the faintest ping of interaction. But year after year, they return nothing but silence. The silence, however, is telling. For some scientists, it suggests that maybe dark matter isn't a particle at all. Maybe it's a sign of gravity itself behaving differently on cosmic scales. Radical? Yes. But science moves forward by questioning even its most cherished assumptions. What makes this detective story so captivating is that every null result, every contradiction, pushes us closer to an uncomfortable possibility. Maybe the Big Bang, as we've told it, is an incomplete story. Maybe it's only chapter 1 of a much larger cosmic saga. But if the Big Bang story is incomplete, what could replace it? Science rarely leaves a vacuum. When one explanation falters, others rush in to fill the void. One of the boldest alternatives is the steady-state universe, once championed in the mid-20th century. Imagine a cosmos with no beginning and no end, where galaxies drift apart, yet new matter continuously forms to keep things balanced. No singularity, no violent birth, just an eternal stage, endlessly refreshed. Though this model lost ground once the cosmic microwave background was discovered, some modern variations linger, whispering, what if the universe is still eternally self-renewing and we've simply misunderstood the background glow? Then there's the cyclic model, a universe that expands, contracts, and rebounds like a cosmic heartbeat. In this vision, our Big Bang wasn't the first, but just the latest pulse in an infinite rhythm of creation and collapse. Some string theorists suggest that hidden dimensions could drive these cycles, each collapse birthing a new cosmos from the ashes of the last. To many, this idea carries a poetic weight. Creation not as a single miracle, but as an eternal recurrence. And what about the most radical of all, the multiverse hypothesis? Perhaps our universe is just one bubble in a vast cosmic foam, each bubble governed by different laws of physics. In that case, the Big Bang wasn't the beginning of everything, but merely the inflation of our little corner. Somewhere out there, other universes could exist with no stars, no gravity, or even entirely alien forms of matter. Suddenly, the question shifts from how did the universe begin to why does our universe have the rules it does? These ideas aren't just imaginative speculation. They're attempts to make sense of real puzzles. The Hubble tension, dark energy, the silence of dark matter detectors. In the absence of clarity, new narratives rise, daring us to see beyond the traditional script. And here lies the hook. What if the Big Bang is not the origin, but just one chapter in a story far stranger, far older, and far less human-centered than we ever dared to imagine? If the Big Bang is just one chapter, the natural question becomes, who's writing the rest of the book? And here, science itself splits into competing voices. Some insist the Big Bang must remain the opening act, while others dare to rewrite the script entirely. Take the cyclic universe again. It isn't just a poetic metaphor, it's backed by real equations. In the early 2000s, physicists like Paul Steinhardt and Neil Turok proposed the ekpyrotic model, a vision where our universe exists on a brane, a vast cosmic sheet, which occasionally collides with another hidden brane in higher dimensions. Each collision, a new Big Bang. To us, it looks like creation out of nothing, but to the larger cosmos, it's just another impact in an endless dance. Meanwhile, advocates of the steady-state vision never fully disappeared. They argue, why trust a one-off explosion when nature everywhere else prefers cycles, balance, and renewal? If galaxies keep forming, why not imagine matter quietly bubbling into existence from the vacuum? And in today's era of quantum weirdness, where particles appear and vanish in empty space, this doesn't feel as far-fetched as it once did. And then, the multiverse, perhaps the boldest idea of all. Inflation theory, which was originally meant to rescue the Big Bang, accidentally opened the door to an infinite landscape. If inflation can happen once, why not countless times in countless regions? In this picture, our universe is just a lucky accident, one bubble where physics allows stars, planets, and people. Somewhere else, reality might look like nothing we could ever imagine. Yet here's the tension. These models are dazzling, but they're also hard to test. No telescope today can peer into other universes or watch a prior cycle collapse. That makes them thrilling, but also maddening. They live at the border between science and philosophy, where imagination fills the gaps left by data. And so the story of cosmology becomes less like a solved puzzle and more like a courtroom drama. The Big Bang still holds the gavel, but its challengers keep presenting evidence, cross-examining, daring us to doubt. The jury, us, the public, and the scientists themselves, is still deliberating. But what happens when the very tools we use to decide, our telescopes, our measurements, begin to show cracks themselves? That's where the story takes its next turn. But here's the twist. Even if we wanted the Big Bang to remain the reigning story, the universe itself keeps whispering contradictions. The most powerful telescopes we've ever built are no longer just confirming the model, they're poking holes in it. Take the Hubble tension. For nearly a century, astronomers have measured how fast the universe is expanding, the so-called Hubble constant. Simple enough, right? Except it's not. When we measure nearby galaxies with Cepheid stars and supernovae, we get one number. But when we use the cosmic microwave background, the Big Bang's supposed afterglow, we get a very different number. Both methods are precise, both methods are trusted, and yet they stubbornly disagree. It's like having two clocks in your house, both brand new, both ticking smoothly, but one says it's 6 o'clock, and the other swears it's 6:20. Which do you believe? And then came the James Webb Space Telescope. In its very first images, Webb unveiled galaxies so ancient, so massive, and so well formed that they shouldn't even exist if the Big Bang timeline is correct. By the rules of the standard model, the universe simply hadn't had enough time to build such structures. It's as if you walked into a nursery expecting newborns and instead found fully grown adults. The physics doesn't add up. These aren't small technical quirks, they're gaping cracks. If our most trusted instruments can't reconcile the story, then perhaps the story itself needs rewriting. And here's where things get even more provocative. Some scientists now wonder if the Big Bang model has been patched so many times that it's becoming less of a clean theory and more of a Frankenstein's monster, stitched together to keep it alive. Dark matter, dark energy, inflation, now maybe even early dark energy. Each addition keeps the Big Bang afloat, but at what cost to elegance and simplicity? And this raises a haunting question. What if the data isn't wrong? What if the model is? What if the universe is telling us something far stranger than we're ready to hear? Which brings us to a deeper possibility. Maybe we need to step outside the entire framework of beginning and end altogether. Maybe the cosmos doesn't care for tidy human stories of creation and conclusion. Maybe it's wilder than that. So if the Big Bang falters under the weight of its own contradictions, what comes next? For many scientists, the answer isn't to scrap cosmology, but to imagine something even more audacious. A universe without a true beginning. Think of cyclic models. In these ideas, the universe expands, contracts, and then rebounds, not once but endlessly, like a heartbeat echoing through eternity. Instead of a single explosive birth, we might be living in one of countless cosmic cycles, each erasing and rewriting history in ways we can barely fathom. Or consider conformal cyclic cosmology, Roger Penrose's daring proposal. He suggests that what we call the heat death of the universe, when everything is stretched thin and all stars have burned out, could itself morph into a new Big Bang. In his vision, the end and the beginning are not opposites but the same event, viewed through different scales of time. And then there's the bouncing universe hypothesis, where our cosmos didn't emerge from nothing, but from a prior collapse. A cosmic implosion that triggered the expansion we now call the Big Bang. In this view, the so-called beginning is just a rebound, part of a larger rhythm written into the fabric of space-time. Even wilder still is the notion of an eternal inflation multiverse. Imagine countless universes bubbling up like foam in a vast sea of inflating space. Our universe, the one we measure, the one we think of as everything, would just be one bubble among many. In this scenario, the question of when did it all begin may be meaningless. There was no first bubble, no single spark, just endless frothing creation, stretching without limit. And here's where it becomes dizzying. All of these models aim to explain the same puzzles the Big Bang struggles with. The early galaxies, the Hubble tension, the need for mysterious add-ons like inflation and dark energy. But they also confront us with something profoundly unsettling. If the universe had no beginning, then our search for an origin story might be chasing a mirage. Which leaves us staring at an even bigger mystery. If there was no first moment, no cosmic dawn, then what does that say about time itself? Is time something real, flowing forward like a river? Or is it just another construct, an illusion tied to how we perceive change? If the universe never truly began, then we're forced to confront a question most of us would rather avoid. What exactly is time? We treat it like a constant companion. Ticking clocks, rising suns, aging faces. Yet physics has long whispered a more unsettling story. That time might not be fundamental at all. Einstein gave us our first crack in the illusion. In his relativity, time isn't a universal rhythm but something pliable, bending with speed and gravity. A clock racing on a spaceship ticks differently than one on Earth. Even your wristwatch runs ever so slightly faster at the top of a mountain than it does at sea level. Time, it seems, has no single truth. And if relativity shook us, quantum physics nearly shattered us. At the deepest level, equations describing the universe don't actually require time to exist. Particles don't flow through seconds. They exist in states, probabilities, and interactions. In some formulations, time is little more than a bookkeeping trick, a way for humans to make sense of relationships that exist without any ticking metronome behind them. Here's where cosmology takes the knife's edge even further. If time is not fundamental, then asking, when did the universe begin, could be like asking, what's north of the North Pole? The question itself dissolves, leaving us grasping at shadows. And yet, we live our lives inside the illusion. We age. Stars are born and die. Galaxies collide. Something is giving us the sense of before and after. Some physicists argue that what we call time may emerge from entropy, the arrow of disorder. The universe doesn't march forward because of a clock in the sky. It does so because energy spreads, because order decays, because every star that burns leaves behind a little more chaos. So imagine this. If entropy creates the arrow of time, then in a universe without a beginning, entropy could reset with each cosmic cycle, flipping the arrow, restarting the illusion. To us, each new cycle would feel like a beginning, but in truth, the universe would simply be continuing a dance it's been performing forever. Which raises the most haunting thought of all. If time is only an illusion, then maybe beginnings and endings are illusions too. And that means the death of the universe might not be the final curtain, but just another act. If time itself might be an illusion, then so too is the idea of a single, final ending. Instead of dying once, the universe may have been reborn countless times, each cycle wiping the slate clean, leaving behind only faint whispers of what came before. This is the essence of the cyclic universe hypothesis. Imagine the cosmos not as a single explosion, but as a breathing organism. Expansion is the inhale, contraction the exhale. Each cycle creates new galaxies, new stars, new worlds, while the ashes of the old dissolve into silence. Ancient cultures seem to sense this rhythm. The Hindu concept of kalpas speaks of universes born and destroyed across unimaginable spans of time. The Stoics envisioned the cosmos periodically consumed by fire, only to rise again like a phoenix. And today, modern physics has cautiously revisited these ancient intuitions. One version, the ekpyrotic model, suggests our universe may be the result of two higher dimensional brains colliding in a timeless void. Each collision births a universe, expands it, then leaves it to collapse before the cycle begins again. In this view, the Big Bang wasn't the start of everything. It was just our turn in an eternal chain. And then there's the Big Bounce. Instead of a singular beginning, the cosmos might endlessly oscillate, shrinking into a dense state and then rebounding outward in another expansion. Every universe would carry echoes of the one before it, subtle fingerprints embedded in the cosmic microwave background, like whispers from ancient universes hidden in the radiation we measure today. But here's the twist. If cycles are real, then everything you see, the stars, the oceans, even you, may have existed before, in some form, in another round of reality. Perhaps not identical, but close enough that history itself may repeat. The unsettling part? This would mean our universe isn't special at all. It's just one bead on an infinite string, part of a rhythm that has no beginning, no end. A rhythm older than time, older than memory. And yet, despite its elegance, this idea remains controversial. Because if the universe is eternal, then why does the evidence we have, the cosmic microwave background, the abundance of light elements, the expansion of space itself, seem to point so clearly toward a single Big Bang event? That's where we go next. The beauty of cosmic cycles is undeniable, but science demands more than beauty. And this is where defenders of the Big Bang stand firm, because the universe itself has left behind fingerprints that seem impossible to deny. The first, and most decisive, is the cosmic microwave background. In 1965, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon a faint hiss in their antenna, a whisper of heat left over from the birth of the universe. It didn't matter where they pointed their detector, the signal was everywhere, surrounding the Earth in a cosmic afterglow. This radiation is astonishingly uniform, like the dying embers of a great fire. To Big Bang cosmologists, it is nothing less than the echo of creation, the universe cooling down from an unimaginably hot beginning. If the cosmos had no birth, if it were eternal and cyclic, then why does this perfect afterglow still bathe the night sky? Then there's the abundance of light elements. Hydrogen, helium, and lithium exist in the precise ratios predicted by Big Bang nucleosynthesis. This isn't guesswork, it's physics. In the first 3 minutes after the Big Bang, the universe was hot and dense enough to fuse protons and neutrons into these light nuclei. And when scientists compared the predictions to actual measurements, the match was uncanny. Even the expansion of space itself refuses to be ignored. Edwin Hubble's discovery that galaxies are rushing away from us isn't just a curiosity. It's a cosmic rewind button. Run the film backward, and everything converges to a single origin, a moment when all matter, energy, and even space itself were compressed into one primordial state. And so, the defenders of the Big Bang argue, we are not looking at theories or metaphors, we are looking at evidence, real, testable, undeniable. But here's the paradox that keeps cosmologists awake at night. If the Big Bang explains so much, why do some of its predictions feel incomplete? Why do anomalies, subtle irregularities in the cosmic microwave background, unexplained patterns in the distribution of galaxies, still whisper that maybe, just maybe, there's more to the story? And it's in those whispers that the alternatives begin to creep back in. For all its triumphs, the Big Bang model is not without its shadows. And for those who study the sky night after night, the universe sometimes seems to whisper, there's more to me than you think. Take the horizon problem. The cosmic microwave background is astonishingly uniform, the same temperature in every direction. But here's the puzzle. Parts of the universe are so far apart they could never have exchanged information, let alone heat, in the time since the Big Bang. How, then, did the cosmos become so evenly smoothed out, as though stitched by an invisible hand? Then there's the flatness problem. Observations show the universe is geometrically flat, balanced with exquisite precision between collapse and runaway expansion. But why? Any deviation at the earliest moments should have grown into catastrophic extremes. Yet here we are, in a cosmos that behaves as if it were fine-tuned for balance. And the mysteries don't end there. When astronomers map the night sky, they find subtle anomalies in the cosmic microwave background, strange cold spots, faint asymmetries, alignments that shouldn't be there. Are these mere statistical quirks or hints of hidden physics waiting to be uncovered? Even the dark sector of the universe, dark matter and dark energy, feels like a confession that the Big Bang story is incomplete. These invisible forces account for 95% of the cosmos, yet remain beyond direct detection. How can a theory claim completeness when most of the universe is made of things we can't even see? To its critics, these cracks are more than curiosities. They are opportunities, places where alternative ideas might slip in. Could the cosmos be cyclic after all, endlessly reborn in grand oscillations? Could vast fields of plasma, as some physicists once suggested, play a role in shaping the universe's fate? Or are we glimpsing something stranger still? A physics not yet written, waiting to rewrite everything we think we know. The defenders of the Big Bang call these anomalies puzzles to be solved. But to others, they are a challenge, a cosmic dare, and out of that dare, new theories begin to rise. Whenever a great theory shows weakness, challengers emerge. And in the mid-20th century, bold alternatives to the Big Bang began to take shape, each one claiming to explain the universe in ways the standard model could not. The most famous was the steady-state theory. Its champions argued that the universe had no beginning at all. Instead, it was eternal, infinite, and unchanging on the largest scales. Galaxies might move apart, yes, but new matter would continually be created from the vacuum, filling the gaps, keeping the cosmos forever young. It was a daring idea, elegant in its refusal to accept a cosmic birth moment, and appealing in its philosophical symmetry. A universe without beginning also meant a universe without end. Others looked not to new matter, but to new forces. Advocates of plasma cosmology pointed to the power of electricity and magnetism, forces often overshadowed by gravity in astronomy. They argued that vast cosmic currents could shape galaxies, form structures, and even mimic what the Big Bang attributed to expansion. Could the universe, they asked, be a great electrical web, sparking and glowing across infinity? There were still more radical visions. Some proposed oscillating universes, where the cosmos expands and contracts in eternal cycles, each Big Bang followed by a big crunch. In this view, our universe is just one beat in an endless cosmic rhythm, a heartbeat that has pulsed forever. And even stranger ideas crept in, whispers of multiverses, of parallel realms budding off from ours like branches from a cosmic tree. The Big Bang, in this picture, was not unique, but just one among countless others. For a time, these theories stirred real excitement. They promised to solve the horizon and flatness problems, to escape the strangeness of dark matter and dark energy, and to restore a kind of timeless grandeur to the universe. But science is not won by imagination alone. Each new vision had to face the same question. Could it stand against the data? And soon, the universe itself began to weigh in, delivering evidence that would decide which stories would survive, and which would fade into history. For years the debates raged. Lecture halls echoed with arguments, conferences turned fiery, and in journals the battle between Big Bang and its rivals played out like a duel across pages of equations. Could the cosmos really have sprung from nothing? Or was it eternal, endlessly renewing itself? Then, in 1965, the universe itself delivered a clue so startling it silenced many of the loudest voices. Arno Penzias and Robert Wilson, two radio astronomers working in New Jersey, stumbled across a faint hiss of static in their antenna. At first, they thought it was interference, maybe from pigeons nesting inside the dish. But when the noise persisted, no matter where they pointed the telescope, they realized they had uncovered something extraordinary. It was the cosmic microwave background, a ghostly afterglow left behind from the hot, dense birth of the universe. Exactly what the Big Bang model had predicted. The signal was faint, but it was everywhere, wrapping the cosmos in an invisible blanket of ancient light. Suddenly, the steady-state theory, with its eternal universe, had no answer for this relic radiation. The Big Bang had gained its strongest piece of evidence yet, but the universe wasn't finished speaking. Redshift surveys confirmed that galaxies weren't just moving apart. They were receding at speeds that matched the predictions of expansion from a single origin. The further astronomers looked, the faster galaxies fled. The pattern was unmistakable. Space itself was stretching. And then came measurements of light element abundances, hydrogen, helium, and trace amounts of lithium, forged in the first minutes after the Big Bang. The proportions lined up almost perfectly with theoretical predictions. It was as if the cosmos had left behind a recipe card, proof of its fiery beginning. These discoveries hit like hammer blows against rival theories. Steady state lost its footing. Oscillating models grew harder to defend. Plasma cosmology, though imaginative, struggled to match the overwhelming precision of the data. By the late 20th century, the Big Bang was no longer just a theory. It was the dominant narrative, the backbone of modern cosmology. But with triumph came new puzzles. The Big Bang explained much, but not everything. And so, as scientists celebrated victory, they also found themselves staring at fresh mysteries. Clues that suggested the story of the universe's beginning was still incomplete. The discovery of the cosmic microwave background had cemented the Big Bang as the leading explanation. For many scientists, it felt like the case was closed. Humanity finally had its origin story. Everything, everywhere, all at once, born in a single burst of unimaginable heat and light. But science has a way of humbling certainty. The deeper astronomers looked, the more cracks appeared in the triumphal narrative. One puzzle came from the very glow that confirmed the Big Bang. That background radiation was astonishingly uniform, the same temperature in every direction. But if the universe had expanded from a tiny point, how did distant regions that were never in contact with each other end up so perfectly balanced? This was the horizon problem. Regions too far apart to exchange energy somehow looked identical. Then there was the flatness problem. Measurements suggested that the geometry of the universe was eerily close to perfectly flat, balanced on a cosmic knife's edge between eternal expansion and catastrophic collapse. Any tiny deviation at the beginning should have amplified over billions of years, yet the universe seemed finely tuned, as though it had been set up with impossible precision. And perhaps most perplexing of all, galaxies themselves. Their stars moved in ways that visible matter couldn't explain. It was as if something unseen, something massive and invisible, was holding them together. This became the first compelling hint of dark matter, a substance that doesn't shine, doesn't reflect, but outweighs everything we can see. And beyond that lurked dark energy, a force even stranger. Far from slowing down under its own gravity, the universe's expansion was actually accelerating. Something hidden in the fabric of space itself was pushing galaxies apart faster and faster, rewriting the ending of cosmic history. Each discovery deepened the paradox. The Big Bang had won the argument, but it hadn't answered the most profound questions. In fact, it had raised new ones. Questions so strange they threatened to reshape physics itself. And so, the story of the universe entered its next chapter, one of invisible forces, elegant fixes, and bold new ideas that would either save the Big Bang or break it. Just when it seemed the Big Bang might crumble under its own paradoxes, a radical new idea emerged, one so audacious it reshaped cosmology almost overnight. What if, in the tiniest fraction of a second after its birth, the universe didn't just expand, it exploded outward in a breathtaking surge of speed, stretching space itself faster than the speed of light? This was the theory of cosmic inflation, first proposed in the early 1980s. It wasn't just an add-on to the Big Bang, it was a rescue operation. Inflation explained why the universe looks so uniform, why it appears so flat, and how tiny quantum jitters in the earliest moments could later blossom into galaxies, clusters, and the vast web of cosmic structure we see today. Imagine a balloon being inflated so rapidly that any wrinkles vanish in an instant. That's what inflation does to space-time. Those faraway regions that once seemed disconnected. Inflation says they were once right next to each other, smoothed and stretched before drifting apart. For many physicists, it felt like a masterstroke, a theory that patched nearly every hole in the Big Bang model in one sweeping gesture. Suddenly, the horizon problem and the flatness problem weren't cosmic accidents. They were the natural outcome of an early, furious expansion. But this solution came with staggering implications. If inflation is real, it didn't just happen once. Many versions of the theory suggest it could happen again and again, in endless cycles, spawning countless universes in a vast cosmic multiverse. Ours would be just one bubble in an infinite frothing sea. It was thrilling, dizzying, and deeply unsettling. Because if inflation is correct, then the Big Bang wasn't the beginning at all. It was merely a local event in a grander, stranger reality, one that may never truly have a beginning or an end. And that left scientists with a haunting thought. Had they solved the mystery of the universe's birth, or had they stumbled onto an even deeper enigma? If inflation really happened, then the story doesn't stop with our universe. In fact, it may be just the beginning, because inflation doesn't necessarily shut off everywhere at once. Picture boiling water. Bubbles appear here and there, each one expanding, each one forming its own little world. That's what some versions of inflation suggest. Our universe is just one bubble, born when inflation stopped in a tiny patch of space. Meanwhile, beyond our cosmic horizon, new bubbles keep forming, endlessly. This is the multiverse hypothesis, a cosmos not of one universe, but of many. Each bubble could have its own physical laws, its own constants of nature, even its own versions of physics. Some might be barren voids, others could be teeming with unimaginable forms of matter and energy. And in this vast ocean of universes, ours would be just one quiet drop. It sounds like science fiction, yet it emerges naturally from inflationary theory, as if the mathematics couldn't resist pushing us into stranger territory. And this raises a question so profound it borders on the philosophical. If the multiverse exists, can we ever truly understand our place in reality? For scientists, the multiverse is both exhilarating and troubling. On one hand, it could explain why our universe seems so perfectly tuned for life. In a sea of infinite variations, at least one bubble would have the right conditions. On the other hand, it threatens to pull cosmology out of the realm of science and into speculation. Because if other universes are forever beyond our reach, how could we ever test the idea? And yet, hints keep appearing. Some researchers search for subtle fingerprints in the cosmic microwave background, tiny scars that might betray collisions between universes. Others argue that quantum mechanics itself almost demands a multiverse, that every possibility is realized somewhere in an endless branching of realities. But the real tension is this: if the multiverse is real, then the Big Bang wasn't the ultimate beginning. It was just one chapter in a story far larger than we can imagine, and maybe one we'll never finish reading. If the multiverse is more than just a bold idea, then surely, somewhere, there must be fingerprints left behind. And so, cosmologists have turned their gaze back to the faintest light in the universe, the cosmic microwave background, that relic glow from the dawn of time. This afterglow isn't just ancient. It's a cosmic photograph taken when the universe was only 380,000 years old. And on it, scientists hope to find subtle distortions, tiny scars in the fabric of space-time that might hint at something extraordinary. Perhaps even collisions between bubble universes. Teams using satellites like WMAP and Planck have mapped this light in exquisite detail. What they've found is astonishing. A universe, nearly uniform, but with delicate ripples that seeded all galaxies, stars, and planets. Yet within that near perfection lurk anomalies, cold spots, unexplained asymmetries, features that refuse to fit neatly within the simple picture of a lone Big Bang. Some researchers suggest these could be statistical flukes. Others whisper, what if they are evidence of something bigger? Perhaps signs that our universe brushed against another bubble long ago. Even more ambitious is the hunt for primordial gravitational waves, ripples in space-time itself generated in the chaos of the universe's earliest moments. Detecting them would be like hearing the universe's birth cry, direct proof of inflation. Projects like BICEP-2 once claimed such a detection, only to have the signal fade into dust. Literally, cosmic dust in our own galaxy, mimicking the pattern. Still, the search continues, with new instruments more sensitive than ever before. And here's the hook. Every new dataset seems to tease us. Enough consistency to confirm our models, enough anomalies to keep us questioning. The universe, it seems, is daring us to keep looking, dangling the possibility that the answers lie just at the edge of what we can measure. If these scars, ripples, or echoes ever confirm inflation, or even hint at other universes, it would be the most profound discovery in human history. But until then, we are left listening to whispers from the cosmic dark, trying to decide whether they are echoes of our own imagination or the first faint signs of a reality far stranger than we dared to dream. For a moment, it seemed as though the whispers had turned into a shout. In 2014, scientists from the BICEP-2 experiment announced they had seen it. The long-sought primordial gravitational waves, the smoking gun of cosmic inflation. The news was electric. Headlines declared a Nobel Prize discovery. It was the kind of moment that could rewrite textbooks overnight, proving the Big Bang's inflationary beginning beyond doubt. The images they released showed a swirling pattern etched into the microwave background, as if the very fabric of space-time still trembled from the first fraction of a second of existence. But the excitement didn't last. Other teams scrutinized the data, and what they found was humbling. The signal wasn't from the universe's birth cry at all. It was from dust. Tiny grains of interstellar material within our own Milky Way had mimicked the very signature scientists were chasing. The smoking gun dissolved into smoke and mirrors. This wasn't the first disappointment, nor would it be the last. Again and again, cosmologists find themselves chasing clues only to discover they've been tricked by nature's static, by the noise of instruments, or by patterns too faint to trust. And yet, every failed attempt sharpens the next. But here's where the story deepens. Even in failure, anomalies remain. That strange cold spot in the microwave background, the uneven distribution of matter across billions of light years, fluctuations in cosmic expansion that don't quite match predictions. Each puzzle piece hints that perhaps our model of a single, clean Big Bang is incomplete, and so the search turns from dust-filled false alarms to more radical questions. If inflation can't be cleanly proven, could it be that our universe began in an entirely different way? Could it be that the story of cosmic birth isn't a singular explosion, but a cycle, a rhythm, echoing across eternity? Because as one door closes, the dream of a definitive smoking gun, another door opens. The possibility that what we think of as the beginning might not have been the beginning at all. What if the universe never truly began at all? What if the Big Bang was not the first moment, but merely the latest chapter in an unimaginably long story? This is where science brushes shoulders with philosophy. Some physicists have suggested that the cosmos could be cyclical, a universe that expands, slows, collapses, and is reborn in a new explosion, over and over, forever. To us, the Big Bang would feel like a singular event, but in reality, it could just be the latest heartbeat in an eternal rhythm. The idea is not new. Ancient cultures often imagined the cosmos as cyclical. From Hindu cosmology with its endless cycles of creation and destruction, to the Stoic philosophers who envisioned the universe burning and reforming in eternal fire. And now, modern physics has begun to circle back to the same haunting question. Was the bang truly the beginning, or just another bounce? Evidence, though faint, whispers in this direction. Those anomalies in the cosmic background, the cold spots, the irregularities, might be echoes, scars left behind by a universe that has been through more than one birth. Certain models of quantum gravity even allow for a big bounce, where instead of an ultimate singularity, the universe contracts to an incredibly dense state, then rebounds, seeding the expansion we see today. It's a radical vision, one that strips away the comfort of a clean beginning. Because, if true, it means the question of what came before the Big Bang has no answer. There was always a before, always another universe giving way to this one, and beyond us, another waiting to be born. This is where the story shifts, no longer about a single event, but about an endless cycle, where creation and destruction are woven together like night and day. And it forces us to wonder, if the universe is eternal, what role do we, a species born in just one cosmic heartbeat, truly play in the grand cycle? Imagine the universe not as a straight line with a sharp beginning, but as a cosmic heartbeat forever pulsing between contraction and expansion. To the naked eye it feels poetic, but to modern physics this is more than poetry. It's a serious possibility. Enter loop quantum cosmology, a branch of physics that tries to unite Einstein's relativity with quantum mechanics. Where relativity says a collapsing universe should crunch into an infinite singularity, a point of infinite density, quantum theory says, not so fast. At the smallest scales, space itself may be granular, like pixels on a screen, and those quantum pixels could prevent the universe from ever shrinking to nothing. Instead of ending in a singularity, the universe would rebound. That rebound, a big bounce, could be what we mistake as the Big Bang. What we call the beginning might really be a transition point, one in an infinite chain. Here's where the story becomes stranger. If this theory is true, the irregularities we see in the cosmic microwave background, those faint ripples frozen into the oldest light, could be fossil records of a previous universe. Not just a universe like ours, but our universe's parent. Imagine that. We may be studying not only the aftermath of our Big Bang, but also the scars of one that came before. But this idea isn't without its challenges. Critics argue that evidence is thin, and that each bounce would erase too much information for us to ever confirm the cycles with certainty. Still, the possibility refuses to die, because if the Big Bang wasn't unique, then the cosmos is far older, far stranger, and far more eternal than we dare to believe. And this leads us to an even more radical thought. If universes can bounce, can they evolve? Could each cycle refine the conditions for life, like nature's most ambitious experiment? If the Big Bang wasn't the absolute beginning, but just the latest rebound in an endless chain of cosmic cycles, then another question rises. Do universes evolve the way life does? Think about it. In biology, natural selection works because living things reproduce with variation, and those variations that survive get carried forward. Could the cosmos itself work under a similar rule? This is where the provocative idea of cosmological natural selection enters the picture. Some physicists, most notably Lee Smolin, have suggested that black holes might be more than just destructive pits of gravity. They could be cosmic wombs, places where the fabric of space-time pinches off and gives birth to new universes. Each baby universe might inherit slightly different physical laws than its parent. If that's true, then universes that are good at making black holes would reproduce more often. Over countless cycles, only those universes with the right physical constants, the right balance of gravity, matter, and energy, would dominate. In other words, the universe we live in could be the result of an evolutionary process on a cosmic scale. And here's the twist. That might explain why our universe seems so finely tuned for complexity and life. Not because it was designed, but because only universes like this one survived the trial and error process across countless cycles. But this idea isn't just poetic, it's testable, at least in principle. If Smolin's hypothesis is correct, we should expect our universe to be optimized for producing black holes. And surprisingly, many astrophysical models suggest that's exactly the case. Of course, not everyone agrees. Some argue it borders too closely on metaphysics, or that it simply shifts the mystery back a step. Who set the rules of the evolutionary game itself? But even skeptics admit the notion of a self-replicating cosmos reframes our place in it. We aren't just residents of a single, fleeting universe. We may be the children of an infinite cosmic family tree. And if universes can evolve, could they also interact? Could the fingerprints of another cosmos leak into ours? But what if universes don't live quietly in isolation, each sealed off from the rest? What if they can touch, even collide, leaving scars that we can still see today? In 2010, a team of cosmologists studying the cosmic microwave background, the faint afterglow of what we call the Big Bang, thought they had found something strange. circular bruises in the pattern of radiation, subtle distortions that didn't match the predictions of a perfectly smooth inflationary model. The claim was controversial, but the interpretation was breathtaking. These could be the fingerprints of another universe brushing up against ours in the distant past. Imagine two bubbles forming side by side in a cosmic froth. Eventually, their expanding edges bump into one another, warping their shapes. If our universe is one bubble in a frothing multiverse sea, then maybe those anomalies in the sky are the faint echoes of a cosmic collision event. And here's where it gets even more intriguing. Some physicists argue that this might not just be speculation. Certain models of eternal inflation, the idea that space itself is constantly inflating, spawning new universes endlessly, predict that collisions are not rare at all. In fact, they might be inevitable. If true, our universe may carry the battle scars of ancient encounters. These echoes could appear as cold spots, rings, or distortions in the microwave background, faint but measurable reminders that we are not alone. Of course, the data is maddeningly ambiguous. The bruises could just as easily be random fluctuations, quirks of statistics, or even subtle contamination from our own galaxy. Yet, the allure persists, because the stakes are enormous. Detecting even a hint of another universe imprinted on our sky would transform cosmology overnight. It would mean the Big Bang wasn't the ultimate beginning. It was just one local spark in an infinite cosmic fireworks show. And then comes the deeper question. If other universes have brushed against ours, did they leave more than bruises? Could the laws of physics themselves, the very constants we take for granted, have been nudged, shifted, or rewritten by a neighbour's influence? Some daring theorists suggest that the fine-tuning problem, why the constants of nature seem perfectly balanced for stars, galaxies, and life, might be explained not by design or chance, but by these subtle interactions. Perhaps our cosmos was gently edited long ago, shaped not just by its own birth, but by contact with worlds beyond. And if echoes of other universes linger in the background radiation, what might that mean for the future? Could another collision still lie ahead, rewriting everything we know in a single, universe-shattering instant? Picture the night sky you know so well. The constellations, the Milky Way, the faint glow of distant galaxies. Now, imagine all of it, every star, every atom, every rule of physics itself, suddenly rewritten in an instant. That's the terrifying possibility some cosmologists whisper about when they talk about future collisions between universes. It's not just science fiction. In models of eternal inflation, new universes are constantly bubbling into existence within a vast, inflating multiverse. They don't remain politely apart. Eventually, some expand into each other's territory, and when two universes collide, the results are not gentle. For the inhabitants inside, if there are any, it could mean the end of everything familiar. Physicists imagine it like two expanding soap bubbles slamming together. At the point of contact, energy floods the boundary, and the structure of space-time itself can be reshaped. From inside, that could look like a sudden wall of annihilation racing toward you at nearly the speed of light, unstoppable, unseeable until it's too late. Entire galaxies would vanish as if they had never been, replaced with whatever exotic laws govern the intruding universe. This might sound purely catastrophic, but some theorists take a different view. They wonder if such collisions could also be creative events, birthing entirely new physics, or perhaps hybrid universes with blended properties. The strange patterns some claim to see in the cosmic microwave background, those bruises and circles, may be the fossilized remnants of just such an encounter long ago. If that's true, then we are already living in a universe shaped by collision, and the fear becomes fascination. What if a future collision doesn't just erase us, but transforms us? What if universes crashing together are the cosmic equivalent of tectonic plates colliding, sparking mountains, earthquakes, and new landscapes? Only on a scale that reshuffles the very rules of existence. Here's the catch. We'd never see it coming. The collision front would move at light speed, and no telescope could warn us in time. One moment, the universe is as it always was. The next, it is fundamentally, irreversibly different. This idea forces us to reframe what safety means in cosmology. For centuries, humans feared comets, asteroids, or supernovas as existential threats. But against the possibility of a multiversal collision, those dangers are trivial. If these models are correct, then the biggest threat of all is built into the fabric of reality itself. So the question lingers like a quiet thunder in the background. If universes can collide, could we already be living in the aftermath of one? And if so, what clues has it left behind, hidden in plain sight? If you were a detective searching for the fingerprints of another universe, where would you look? You can't scour mountaintops or dig through ancient ruins. The evidence, if it exists, must be written across the largest canvas we have, the cosmic microwave background. That faint afterglow of the Big Bang, frozen into the sky like an ancient fossil. And here's where it gets strange. For decades, scientists have noticed something odd in this cosmic wallpaper. There are cold spots, circular patterns, and asymmetries that don't quite fit the clean predictions of standard cosmology. Some researchers argue they're just noise, statistical flukes, but others suggest they could be the bruises of cosmic collisions, scars left over from our universe brushing against another bubble billions of years ago. One famous anomaly is the so-called cold spot in the southern hemisphere of the sky. It stretches across an area far too large to be easily explained by random fluctuations. Could it be the lingering echo of a universe-sized impact? Some physicists think so, proposing that the cold spot may be the smoking gun of a bubble collision in the early inflationary period. But that's not the only clue. If universes collide, they don't just leave one mark. They should imprint multiple concentric circles of disturbance, faint but detectable with the right instruments. Teams using data from NASA's WMAP and the Planck satellite have scoured the cosmic background for these telltale patterns. And while the results are hotly debated, the very fact that mainstream physicists are asking the question shows how serious the idea has become. And it doesn't end with the microwave background. Some astronomers believe the distribution of galaxies itself may carry hints of a hidden collision. Vast voids, superclusters, or unusual alignments could be the fingerprints of an early cosmic brush. Imagine the universe as a frozen pond, smooth in most places, but with ripples and cracks spreading out from where a stone once struck. Yet, for all these tantalizing hints, certainty remains elusive. The problem is that cosmology deals in probabilities, in shadows cast by ancient light. Was that cold spot a glitch in measurement, or was it the cosmic equivalent of a scar, proof that our universe is not as isolated as we once thought? Here's the twist. Even if we confirm such evidence, it doesn't just rewrite physics, it redefines us. Because if we are living inside the aftermath of a cosmic collision, then our very existence, our galaxies, our stars, our Earth, is not the product of one universe, but of two universes smashing together long ago. And that leads us to the next question. If the sky is scarred with the memory of a collision, then what does it say about our future? If the universe carries bruises from past encounters, then we must ask a terrifying question. Are we safe from the next one? It's easy to imagine bubble universes as distant curiosities, like far-off galaxies we'll never reach. But the strange truth is this. In the inflationary model of reality, universes don't just exist out there. They grow, expand, and sometimes they collide. Think of it like soap bubbles on the surface of a sink. Some last quietly, drifting apart. Others merge violently, leaving ripples that spread across the foam. Now imagine that sink isn't a kitchen, but the multiverse itself. Our universe is one bubble among countless others. Statistically, collisions are inevitable. The only question is when, and what would they do to us? Some physicists believe that if another universe were to slam into ours today, the event would be catastrophic. The laws of physics could be rewritten in an instant. Imagine gravity no longer working as you know it, atoms refusing to bond, or even time itself being reset. From our perspective, it would feel like annihilation, the end of everything. But here's the paradox. We might not notice until it happens. A bubble collision would sweep across space at the speed of light, invisible until it arrives. There would be no warning, no chance to prepare. One moment you're sipping tea, the next, reality itself has been rewritten. And yet, there's another side to this. Some cosmologists speculate that not every collision would mean destruction. In certain scenarios, universes could merge more gently, blending their physics together like two rivers meeting. Instead of annihilation, such an event might bring new laws, new constants, even new possibilities for life. What seems like an apocalypse to us might simply be the next stage of cosmic evolution. This possibility is haunting, because if our own universe already bears the scars of an ancient collision, then perhaps we are not doomed by it. Perhaps we were born because of it. Maybe life exists here, on this small blue planet, precisely because two realities merged and rewrote the rules in just the right way. So we are left balanced on a knife edge of wonder and fear. The cosmos could erase us in an instant, but it may have also created us in the first place. And that leads us to a deeper question, one far more unsettling than physics alone can answer. If collisions are inevitable, does that mean existence itself is fragile or infinite? What if everything you know, your memories, your body, even the stars themselves, exist only because the laws of physics haven't yet changed? We like to imagine the universe as stable, governed by rules so firm they feel eternal. Gravity keeps our feet on the ground. Atoms bond in predictable ways. Light travels at a fixed speed. But here's the truth physicists quietly admit. These constants might not be constant at all. They are agreements written into the fabric of our universe, and like any agreement, they could, one day, expire. Take the idea of vacuum decay. Picture the universe as resting inside a shallow valley, stable, but not truly safe. Somewhere out there, in the vast cosmic landscape, there could be a deeper valley, a true vacuum. If a single particle were to tunnel into that lower state, it would trigger a chain reaction faster than light. A bubble of this new vacuum would expand, rewriting physics as it went. In that instant, the universe as we know it would vanish. Chemistry would collapse. Stars would snuff out, and life, all life, would be erased. And like the bubble collisions we explored earlier, there would be no warning, no flash, no siren, no countdown. One heartbeat you exist, the next you don't. It sounds like science fiction, but it's an idea born from real equations. Serious physics debated in research papers. Even Stephen Hawking once suggested that the Higgs field, discovered in 2012, could be a sign that our universe is perched precariously, balanced on a false vacuum. Yet here's the paradox. If such a collapse were likely, wouldn't it have happened already? The fact that you're hearing this now suggests something else may be at play. Perhaps the universe is more stable than we fear. Or perhaps we're simply lucky. But luck isn't a comforting foundation for existence. And this is where the story turns strange. Because if we are living on borrowed time, it changes how we view our place in the cosmos. Instead of eternal permanence, our universe becomes a fleeting, fragile miracle. Every sunrise, every laugh, every fleeting dream exists only because the cosmic rules haven't shifted. Yet. And that brings us to a thought that's both chilling and profound. If existence is this fragile, maybe its value doesn't lie in permanence at all. Maybe its value lies in the fact that it could end, and yet it still happened. If the universe is fragile, then why does it seem so perfectly set up for us to exist? It's one of the strangest paradoxes in all of science. On one hand, physics suggests we could be wiped out without warning by something as exotic as vacuum decay. On the other hand, the very same equations reveal an almost miraculous precision in the conditions that allow life to emerge in the first place. Think of it this way. Every constant in physics, the strength of gravity, the charge of the electron, the mass of the proton, has to fall within an unbelievably narrow range. If gravity were just a little stronger, stars would burn too fast, collapsing into black holes before life could even begin. If it were weaker, stars wouldn't ignite at all, leaving the universe cold and lifeless. The same goes for chemistry. Shift the balance of the strong nuclear force by even a fraction of a percent, and atoms themselves would unravel. And yet, here we are, breathing, thinking, asking questions about why the universe seems so unlikely to exist. This is known as the fine-tuning problem. Some scientists lean toward a stark conclusion. Maybe there's nothing mysterious at all. We exist in a universe tuned for life simply because only in such a universe could beings like us evolve to wonder about it. This idea is called the anthropic principle, a reminder that our perspective is biased. Out of countless possible universes, we could only ever find ourselves in one that works. But others see something deeper. If the cosmos is like a lottery, the odds of hitting a life-friendly jackpot are so tiny, it almost begs for explanation. Could there be other universes, a multiverse, each with its own physical rules, most barren, but a few rare ones sparking life? Or is fine-tuning itself a clue, a cosmic signature pointing towards some underlying order we don't yet understand? This puzzle isn't just abstract philosophy. It has teeth. Every time scientists run new measurements of the cosmic microwave background, of particle interactions inside the Large Hadron Collider, of the spread of galaxies across billions of light years, they're asking the same implicit question. Is the balance holding steady, or are the cracks beginning to show? Because if fine-tuning is real, then the greatest mystery may not be why the universe might one day end, but why it began in such a narrow window that allowed life to flicker on in the first place. And that brings us to the next turn in our story. If fine-tuning is so unlikely, could there be hidden evidence that our universe is just one bubble among many? What if the universe you know, with its galaxies, its stars, and even your own life, is only a single bubble in a far greater cosmic ocean? For centuries, humans assumed that the universe meant everything, one cosmos, one reality. But modern physics has cracked that certainty wide open. Increasingly, the evidence whispers something astonishing. Our universe may be just one of countless others. It starts with a strange idea called cosmic inflation. In the earliest fraction of a second after the Big Bang, the universe didn't just expand, it ballooned at a speed faster than light. This rapid stretching smoothed out the cosmos, explaining why the night sky looks so uniform. But inflation might not have ended everywhere at once. Instead, some regions kept bubbling outward, creating separate pockets of space-time, each with their own laws of physics. This is the multiverse, an endless froth of bubble universes. In some, gravity might be stronger. In others, stars might never ignite. And in a rare few, the constants line up just right, allowing life. At first, this sounded like science fiction, but then came the hints. Tiny temperature ripples in the cosmic microwave background, the faint afterglow of the Big Bang, fit neatly with inflation's predictions. Particle physics, too, adds weight. Theories like string theory require extra dimensions and multiple universes to make sense mathematically. Even black holes, those mysterious regions where space and time break down, suggest that what falls inside may reappear elsewhere, in another cosmic domain. Skeptics argue the multiverse can't be proven. After all, by definition, other universes lie beyond our reach. Yet, the fine-tuning puzzle from the last segment makes this idea strangely compelling. If our universe is just one roll of cosmic dice, then its unlikely balance isn't miraculous. It's inevitable. Out of trillions of universes, one had to look like ours, and we just happen to live in that one. Still, there's something unsettling about this picture. It strips away the uniqueness of everything we know. Earth, the Milky Way, even human history. All of it could be just one version among countless variations. Somewhere, perhaps, a universe flickers where conditions are close but not quite right, and no voices ever rose to wonder about the stars. The multiverse doesn't answer every mystery, though. In fact, it opens the door to a deeper one. If there really are countless universes, then what mechanism, what deeper law is responsible for creating them? And that takes us to our final chapter, the possibility that the cosmos itself may be a kind of simulation, a grand design built on hidden rules we've only begun to glimpse. If the multiverse already challenges our sense of reality, then the final question takes it one step further. What if reality itself is an illusion? This is the simulation hypothesis. The idea that everything you see, hear, and feel might not be the base layer of existence at all, but instead a vast, artificial construct. Not a dream, not a metaphor, but literally a simulation. The argument begins not with science fiction, but with mathematics. Think of how far human computing has come in a single lifetime. In the span of decades, we've gone from blinking arcade pixels to entire virtual worlds. Simulations so detailed that millions of people live digital second lives inside them. Now project that forward 1,000 years, 10,000 years. If a civilization anywhere in the cosmos achieved mastery over computation, wouldn't they have the power to simulate entire universes, complete with conscious beings inside them? That's the unsettling logic posed by philosopher Nick Bostrom. He argued that at least one of these statements must be true. Civilizations never last long enough to reach that level of technology. Or, if they do, they choose not to run simulations. Or, if they do run them, the number of simulated realities would vastly outnumber the real one. And if that's the case, statistically speaking, the odds tilt toward us being inside a simulation right now. Strange clues even tease the possibility. Some physicists studying the very fabric of space-time have suggested it looks pixelated at the tiniest scales, like the resolution of a cosmic screen. The apparent mathematical precision of nature's laws, the way particles obey strict codes, as if following lines of code, seems suspiciously orderly. Even the mysteries of quantum mechanics, where reality only collapses when observed, sound eerily like rendering in a video game engine. Of course, none of this proves we're simulated. Skeptics counter that the hypothesis is unfalsifiable. It can't be tested. Yet the fact that serious thinkers, from Elon Musk to leading physicists, treat it as a legitimate question shows how deeply it resonates with our search for truth. And maybe that's the real heart of it. Whether we live in one universe, a trillion universes, or a carefully crafted simulation, the questions we ask are the same. Why are we here? How does it all work? And what does it mean to exist at all? Perhaps the universe is real. Perhaps it's simulated. Perhaps the Big Bang happened, or perhaps it never did. But as long as there are minds awake in the dark, wondering, imagining and searching, the mystery will never end. And maybe, just maybe, that's the point. So, close your eyes, drift into sleep if you wish, and let the cosmos keep whispering its secrets. Because sometimes, the journey of questioning is the greatest discovery of all.